Telecommunications Standards Development Society, India. On behalf of TSDSI, welcome to the TSDSI Expert Talks series, the second edition, where we will listen to Dr. Kumar Sivarajan on the role of optical networking in the 5G and beyond networks. TSDSI Expert Talk series is a series of webinars that TSDSI is bringing to you with expert speakers, celebrity speakers from all over the world, talking about topics related to 5G, 6G, and related areas, application verticals, etc. This series was kicked off on last month on 24th July with a talk by Professor Paul Raj, where he gave an overview of the 5G ecosystem, the 5G and the 6G ecosystem. And from there on, in the subsequent editions, including today, we will be talking about various aspects of telecom, 5G, 6G, etc. So without further ado, I will just introduce the speakers, Dr. Kumar Sivarajan, and our moderator for today, Professor Kiran Kuchi. Dr. Kumar Sivarajan has been the founder chairman of TSDSI, and he is also the founder and the chief technology officer at Tejas Networks. Professor Kiran Kuchi, who is going to moderate the session today, is with IIT Hyderabad, and he has been spearheading India's activities, research activities and efforts in the 5G standards IMT 2020. And thanks to his tireless efforts, his leadership with a lot of other TSDSI member experts, TSDSI has managed to get our radio interface technology accepted at ITU as one of the technologies, one of the standards for IMT. So over to I'll hand over to Kiran to introduce the topic, and then we start off. Thank you.
Kiran. Thank you, Gundu. Ladies and gentlemen, today we have the privilege of hearing from a distinguished speaker, Dr. Kumar Sivarajan, and this talk will be different from what you heard from the first edition, which is more radio centric by Professor Paul Raj. Now today we will have a very good talk, engaging one on the role of optical networking on 5G and beyond 5G. Dr. Kumar Sivarajan, CTO of Tejas Networks. Kumar was also the founding chairman of TSDSI. He has nearly 3 decades of experience in the field of telecommunications. Prior to joining Tejas, Kumar was an associate professor at IISc Bangalore and a research staff member at IBM Watson Research Center, New York. Kumar holds a BTech in electrical engineering from IIT Madras and an MS and PhD from Caltech, USA. With this, over to Kumar. We can hear from him. Thank you.
Thank you, Kiran. It's a pleasure to be here. Thank you all for joining us late in the evening or today. Let me share my screen to begin. Okay, Kiran, can you confirm my screen is properly visible?
Yes, it is.
Okay, thank you. So I'll talk to you today on the role of optical networking in 5G. And 5G is now old because it's already well into 2020. So I'll touch a little bit upon 6G. We tend to think of all these technologies as being primarily radio, which is true. A lot of the innovation so far has been primarily in the radio sphere. But, there is corresponding innovation in the optical networking as well that has to keep up with every generation. So if you look at, so far the role of optical networking has been backhaul. So if you looked at 2G or 3G, you had a base station which was a few kilometers from your home. It could be as much as 5 or even more. And then you had a microwave backhaul. This was N into 2 megabits or so, and for data, fast Ethernet. And this could actually go a few hops. And then you have an optical network at the very back. It was even common for only a few percent of the cell sites to have optical fiber. So the optical backhaul was kind of limited in 2G. In 4G, I'll skip 3G. 3G was very similar to 2G. In 4G, the data rates went up, so the microwave links got shorter, and it was giggy for the microwave links. The base stations came within a couple of kilometers of your home, and then the backhaul network moved to packet. It used to be SDH earlier, it moves to packet. In 5G, you can expect that the base station will be even closer, except for TSDSI's effort to build a large cell. Larger 5G cells will be small, like 500 meters. So the base station will be very close. All the microwave bands which used to be used for backhaul in 2G and even 4G have now been renamed as millimeter wave and are served for access in 5G. So what's left for wireless backhaul is only some E-band, 70 gigahertz or something. And then the optical transport network has gotten much more complicated in 5G, and I'll talk about that. If you look at the frequency bands, so they have been going up too with every generation. 2G, 3G largely operated in 900 megahertz. In India, we were late with 3G, so we got 3G in 1800 and 2100. 4G, we started with 2300, except then some spectrum became available in 900 and 1800. Otherwise, the spectrum that was auctioned for 4G in India was 23 and 2600 for broadband wireless access. And with 5G, all of that spectrum is exhausted. So we are looking at 3.5 gigahertz in what is called the FR1 band and 28 gigahertz in even higher bands. So the frequencies has been going up. So that also means the cell towers are getting closer to your home, because at higher frequencies you can only have shorter links. The technology for optical has gone from SDH to PTN to optical, the mix of optical technologies and packet technologies today in 5G, which I'll discuss. Okay, so backhaul, I described this. It will be SDH for 2G and 3G, packet transport largely for 4G, and then today we'll have a mixture of OTN and WDM technologies in the backhaul, as well as fronthaul, and I'll describe that. And packet transport is sort of restricted to the first level of base stations. I want to talk about something which is a little bit arcane. The telecom networks needs to be synchronized in both frequency and today also in time. So the old networks used to need only frequency synchronization, so 2G and 3G, and the relative accuracy needed was about 50 parts per billion. And the optical network was called SDH, and that was the primary source of synchronizing all the towers. It was not really GPS, it was SDH timing. In fact, timing was so important and inherent in optical networking that the S in SDH is for synchronous. It's synchronous, digital hierarchy. So synchronization was a very key integral part of optical networking. That went away in 4G, primarily because we started to use optical as a packet transport technologies, and they were not as good as at providing the timing accuracy needed by 4G. There were technologies, SYNC and P2P, SYNC for frequency synchronization, P2P is precision timing protocol for giving you time of day, and time of day was needed for TDD networks. So it's not sufficient to just get frequency synchronization, you also needed time. And while the frequency synchronization requirements haven't gone up, the timing error was less than 1.5 microseconds in 4G. 5G is making the timing error requirement much more stringent, by a factor of 5. So the relative timing between base stations has to be accurate to within 260 nanoseconds. This is just within the limits of what can be achieved by optical technologies today. And actually there are applications in wireless which require even more stringent timing. So for now, The only technology that can provide the required stringency, and I'll say a little bit more about it, is a GPS or our Indian equivalent, IRNSS, I think. So timing is something that attention will come back to. You may ask, why don't we just rely on satellite-based timing for 5G? The problem is twofold. One is a lot of 5G will be indoor. It's not possible to get GPS coverage or any satellite coverage indoor. The second reason is cost. We expect to have 10 times the number of 5G base stations that we had in 4G, and we don't want to burden each of them with a GPS receiver. So clocking standards are receiving a lot of attention simply because we expect to go back to the 2G, 3G era where the optical transport network is providing timing. And there are standards in ITU for both circuit-based transport networks and packet-based transport networks for both frequency synchronization and time synchronization. So if you are interested, you should go and look up what's happening in all of these standards. In terms of the timing accuracy that is needed, in LTE we needed, I said 1.5 microseconds is plus or minus, I think, so 3000 nanoseconds. Category B is timing, which is needed in 5G. It requires 260 nanoseconds of time alignment error. There are more stringent timing requirements. If multiple base stations have to cooperate, two radio units have to cooperate, which are geographically separate. In that case, the timing accuracy needs to be, even more stringent, category A or category A plus. Currently, the challenge in optical networking is to be able to get category A or category A plus timing from the network itself. So I dwelt on timing because I think, technologies have a way of going around in cycles. People forgot about timing, in 4G, thinking everything will happen through satellite. I think that's coming back, and that could be a key area of technology innovation that is needed to make 5G, future release of 5G work very well. So that's why I had this focus on timing. How do you carry time? There's one new innovation in packet networking that has needed to come in order to carry timing traffic. So usually in packet networking, even if you say you have priority, you wait for the packet that is already being transmitted. So even if A has priority over B, if B's packet is under transmission, A waits. So you can think of this as like head of line blocking. If somebody is ahead of you, at least that packet has to get through. This will not do if the timing traffic has to get the quality of service needed in order to get accurate timing. So if you have to meet the end-to-end timing accuracy, you cannot have timing packets, which are usually small packets, wait behind user packets, which are big. So while theoretically, if you've taken networking courses in college or in grad school, you may have heard of preemptive priority in queuing theory. In practice, no networks were implementing preemptive priority. But now, with IEEE's latest time-sensitive networking, preemptive priority is becoming important. So in preemptive priority, if a packet, say user data B is being transmitted and you're sort of partly through it, and if a timing packet comes along, you will stop transmitting B, transmit the timing packet, and then resume transmitting the user data. So this level of higher quality of service for timing traffic is becoming a necessity in 5G. That's more or less what I will have to say about timing. So if you look at the 5G architecture behind the radio, you have backhaul, which is what connects from the core. Then you have, in 5G, you have two more things, Midhaul and Fronthaul. So 5G divides the network into a radio unit, a distribution unit, and a cloud unit. So the network, and after the radio unit is the RF network. Behind it everything is optical. And between the radio unit and the distribution unit, you have the Fronthaul network. Now, Fronthaul has actually seen activity within TSDSI also. TSDSI actually standardized the CPRI Fronthaul standard. I'll talk about that in a minute. So the technologies used in the Fronthaul are OTN. I'll say what that is. It's optical transport networking, but it's not to be used as the common noun. It actually refers to a specific way of doing optical transport networking, but the name is just very generic. And that's a TDM based technology, so time division multiplexing, not packet based. Whereas time sensitive networking, which is an IEEE standard, is a packet based Fronthaul technology, packet transport Fronthaul technology. So these are the two common technologies for Fronthaul. Between the distribution unit and the cloud unit, you have the Midhaul network. This is typically Ethernet traffic. If you say eCPRI or ORAN and all that, they're just different ether types. So basically all the traffic is Ethernet. And this is typically a packet network simply because you have unpredictable amounts of traffic from each location. So you want to do statistical multiplexing. So the first layer of networking, whether you call it Midhaul or Backhaul, is usually packet transport. And deeper in the network, it makes sense that all the backhaul is really OTN, because by this point, the traffic is pretty much steady and there's not much to be gained by doing statistical multiplexing. So in Fronthaul, you need this Fronthaul to take LTE traffic, which is CPRI, option 8, deeper. So it is also possible that as 5G is rolled out, LTE gets deeper by having more radio units. Actually, LTE was also capable of, or is also capable of separating the radio units from the base station sites, and they can actually be 20 kilometers away in CPRI. And so as time evolves, we may even see greater LTE coverage, because there are very, very large number of LTE phones. They're becoming far more affordable, and to increase capacity, operators may decide to take LTE radio units deeper. And that can be done with extending CPRI Fronthaul links. The bottleneck right now is just being able to get fiber in the metros. So if that problem is somehow solved with cooperation with utilities or something, we could actually see a lot of capacity getting built. For 5G, I'll discuss shortly. CPRI is not a good option, so you need to do eCPRI or ORAN Fronthaul. Okay. So TSDSI actually standardized, developed a standard, because that's the charter of TSDSI, for CPRI Fronthaul. And my colleague Jishnu was actually, I think, the chair of the study group, and he was deeply involved in developing the standard. He actually also made this presentation for me. So I'll talk about this in a minute. Then, as I said, the Midhaul standard is IP packet transport networking, and then the backhaul is OTN. Okay, I'll talk about all technologies shortly. So in TSDSI, this is a TSDSI expert talk, so I want to plug for TSDSI. So TSDSI, we've developed a CPRI Fronthaul transport standard. This is capable of carrying both CPRI traffic and Ethernet traffic. Now, Ethernet traffic includes eCPRI, ORAN, Fronthaul traffic, because these are just different ether types. So we define how this would be mapped to OTN using the different mapping procedures available, and how the traffic would also be multiplexed and transported. So at that time, I think the standardization talked about CPRI and Ethernet, but extension to eCPRI and ORAN Fronthaul is fairly trivial, because they're just Ethernet with different ether type. And so that's what we can do. And this Fronthaul standard ensures that we get superior out-of-band time synchronization, which is a property of the OTN technology. Fronthaul. So Fronthaul is what I call standardization run amok. There are too many options. So you have 8 different Fronthaul options, actually more than 8, because once you get to 7, you have 7.2, 7.3, 7.2x, of course 1, 2, 3. So there are a dozen different Fronthaul options. I think so many options is really a hindrance to wider adoption. So I hope the industry picks one or two, preferably one, and makes it a standard. So the goal here is there are many differences of opinion on how you split the RU and the DU. So what goes in the RU? So clearly the physical layer has to go, the RF has to go. If you only put the RF, you get option 8. Then you really send samples of the RF signal, and that's very high bandwidth. You could put part of the physical layer, and that's where the disagreement starts. What is the lower part of the physical layer that you put in the radio unit? What's the rest that goes behind? So I won't go through this. I just want to tell you that it's a messy place, and there are two different approaches also. I mean, in addition to the various options, there's an ORAN based approach which standardizes between the RU and DU not only the user data but also the control plane synchronization and management, most importantly control and management, and therefore it is more of a standard than eCPRI. It's more of an open standard than eCPRI, which only standardizes the data plane. So in principle, then you're on your own on how you're going to do the control and management of the radios. So ORAN is better from the point of view of disaggregating and allowing you, the operator, to deploy multiple vendors, different vendors for the radio unit and the distribution unit. Now, all technology guys want to do everything. So for the Fronthaul or for the Midhaul, which is the F1 interface. So here, this option F1 interface. If you look at 5G, 5G is likely to be deployed closer to your home. So it will be deployed on the street, lampposts is talked about, 500 meters from your home. So the technology that already comes to your home is GPON. All of us pretty much have a broadband connection with GPON, so do I. That's what this is streaming over. And if that's already near your home and the 5G base station is going to be there, the DU, why not use this for Midhaul between the DU and the CU? So the GPON guys have been developing this standard in ITU. So GPON itself is 2.5 gig. So it cannot be used unless your RF bandwidth is very small. So in this chart, I'm showing RF bandwidth at the bottom and MIMO layers on the vertical axis. So, but NG-PON 1, which is 10 gig PON, which is symmetric and the two options, that can do a lot of the Midhaul. So all the green things here, which are sub 10 gigabits, can be done with NG-PON 1. And the next level, which is sub 40 gigabits, can be done with NG-PON 2, which actually goes up to 40 gigabits. So GPON is an option that is being promoted by the GPON folks for Midhaul. And actually, I didn't redo the slides, but now GPON has a 50 gig option. And even this first diagonal of orange is something that GPON is trying to address. Of course, GPON runs out of steam at some point beyond gigabits. The packet transport, I talked about time-sensitive networking for Fronthaul, but even in backhaul, there have to be new advances. So IP, along with MPLS, has sort of been the mainstay of backhaul transport. With 5G, there are a few additions that need to happen. So you need, I'll talk about that. You need to support network slicing in 5G. So the backhaul network has to be capable of network slicing, which means it needs to support L3 VPNs and segment routing. So you need L3 VPN support because you'd have multiple services being supported on the same network, each with its own QoS. So it's also through the backhaul network. So IP-VPN technology is needed. You also need segment routing. I'll tell you in a minute, in very briefly what this is. So let's say you need to go from A to Z. Okay, so the central path computation engine. So this is all SDN, software defined networking. So central agent has a view of the whole network, but it is not going to make micro decisions on how the packets have to get from A to Z. It simply says go from A to C, from C to O, and O to Z. So it basically says avoid D indirectly. Maybe D is going through, maybe D has a fault, or maybe D goes through enemy territory or something. So it just says just do A to C, C to O to Z, and then when the packet gets to A, the distributed protocol within what they call the routing protocols will figure out how to get the packet from A to C and C to O and O to Z. So that's what segment routing does. It sort of combines a high level of abstraction of directing the route approximately through multiple segments and then letting the micro decisions being made by the routing protocols.
Kumar, we can't see the slides. Sorry to.
Oh, we can't see the slides? Okay.
I don't know if it's the case with other. There is a comment also.
Dr. Kumar, could you just refresh your screen and then start sharing again? It will come back.
Okay. Do I stop sharing?
Yes, please, and then restart.
Okay. How about now? Do you see this?
It's coming up, I think. Yeah, good to go.
Good to go. So where did you lose me?
I think one slide back maybe.
This one? Or this one? Or this one?
No. Just go to the next slide, and I think we can start here. Yeah.
Okay. So I was just saying that in the backhaul, I talked about new IEEE standard for fronthaul, time-sensitive networking. For backhaul, it's really been IP and MPLS for a long time. But with 5G, you have network slicing added, and network slicing means you need QoS throughout, including in the backhaul network. And so you need a few different capabilities, which is L3 VPN and segment routing. Okay. Can you see this slide now?
Yes.
Yes, okay. So L3 VPN is very well known. It just means that you need multiple services to be carried with QoS. So that's to be introduced in the backhaul network. Segment routing is the new technology. Essentially, a central agent makes a high-level decision about the route the packet should take, which simply says go from A to C, C to O, and O to Z. So in this picture, and this picture wouldn't have made sense with what I told you before. So the central agent, it's a central agent because today in carrier networks, software-defined networking is being widely implemented, which means there's a central view of everything in the network. So a central agent can compute the path from any place to any place, but you don't want to take this too far and compute the complete, detailed path. So what segment routing does is to abstract this and say the central path computation engine will simply give you a high-level view, saying go from A to C, C to O to Z, which is imposing some policy that you want to avoid going through D. Maybe D has low capacity or D is something to be avoided. And then the detailed routing protocols, what are called IGP, BGP protocols, will compute how to go from A to C, how to go from C to O and O to Z, right? So that is segment routing. So this is becoming popular in 5G, so for the backhaul network. Can you see this picture? I'll keep checking, unfortunately. Okay, can you hear me? It's good to get feedback. Hi, can anyone hear me? Panelists?
Yes, Dr. Kumar, we can hear you.
Okay, fine. So I just want to know before I continue. Okay. 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 So I would say the most interesting technology for backhaul and fronthaul is OTN. Okay, so OTN is, I would say, heavy duty optical networking technology. It makes use extensively of WDM. It supports bit rates today that goes up to 600 gig and probably even higher in future. There have been 3 generations of OTN. I do hear an echo, so maybe some of the panelists can mute. Okay. So OTN 1.0 did only 10 gig, and OTN 2.0 was up to 100 gig. In OTN 3.0, we go up to 400, even beyond, even 600 gig with FlexO. So this technology is sort of scaled up to deliver very, very high capacities over fiber. It's deterministic and it's ultra low latency support, the kind that's needed by 5G. Okay. I'll just give you an idea of sort of what's done, just to emphasize the similarity also to RF. So OTN has, in a 50 gigahertz channel, does 28 giga baud with 2 polarizations, horizontal and vertical, 8 bits per symbol, 256 QAM, and achieves 448 gigabits. And for getting 448 gigabits with practically no error, in optical the goal is 0 error. Okay. So you need an OSNR of almost 32 dB. So you can see from here that the modulation schemes, technologies in optical are very similar to wireless. So you have the same QAM going up to 256 QAM, and you have 2 polarizations, except the capacities are way higher, right? So on an order of magnitude or higher than what you see, or maybe 2 orders of magnitude higher than what you see in wireless. The distances are also very large. So optical technologies are capable of going across oceans. So depending on the modulation technologies used, even you can choose the technology such that you can even go 10,000 kilometers. So you have a trade-off of baud rate, data rate, and distances. So optical technology, but underlying technologies are still similar modulation schemes, error correction codes with turbo codes, I think, which is also used in wireless, and use of 2 polarizations. So those technologies are similar. What I want to tell you more or less in conclusion is that your 5G RAN, except for the last hop, is mostly optical. So all of the fronthaul, midhaul, backhaul is entirely optical. While you mostly hear about the RF technologies, they only go the last few hundred meters of your 5G network, except in TSDSI, which has kept a 5-kilometer intersite distance. It has enabled that through its RIT proposal in ITU and its proposals in 3GPP. But otherwise, 5G is mostly an optical network. 6G, I've not said anything much, but every 10 years, ITU decides that you need a new generation. So LTE was in 2010, IMT 2020 was 5G in 2020. Now you have NET 2030, which is in 2030. And that is what we would colloquially call 6G. Now all the spectrum's gone, so 6G will be even more optical. We already used up FR1, FR2, so up to 60, 70 gigahertz is gone. So you presumably will have something which we call FR3, which operates above 52 gigahertz and will be less than 100 meters. So at that frequency, that means it's just line of sight. So it's even less than Wi-Fi. And I also want to tell you that at this point, that the entire optical spectrum is only 4 terahertz. I mean, 4 terahertz look like a lot, but now with the capacity crunch, it's only 4 terahertz. It's also using all the modulation of 256 QAM and above and multiple polarizations. The key to 6G will be, like in 5G, success depends on scheduling resources and providing capacity on the radio network to all users, dynamically. The same end-to-end scheduling and QoS dynamically, which I forgot to add in the optical network, which will be what will cause the 6G network to be a successful one. Because with limited bandwidth, and I'm telling you 4 terahertz is limited in 2030, you cannot afford to give resources all the time to everybody. So optical will be as dynamic as the wireless network today. You will allocate this precious bandwidth dynamically on a need basis, and the technologies that you've invented for RF will be useful in optical. So if you're an RF today and you're not retiring by 2030, look for jobs in 6G in optical. I will stop here. Thank you.
Thank you, Kumar. That was quite a nice spin to 5G and 6G being optical. The way we want to do it now is that I do have a set of questions I would like to ask you, but I also want to take up questions from the audience. I request them to type the questions on the questions pane. There are a few, but I encourage them to write down their questions. In the meantime, I'll go ahead and ask you a set of questions. Then we'll go on a couple of 5-10 minutes, and then we'll take questions from the audience. Okay. So quite an interesting talk. Being a radio engineer, we sometimes tend to ignore the other aspects. There's so much more to be done. So let me ask a few specific questions. You talked about timing and synchronization. What is the importance with respect to TDD, which is the predominant use case in 5G?
Right. So, in TDD, it's because of time division duplexing. All the radios need to be accurately aligned in time. And if you're doing, even fancier schemes like interference cancellation, like the ones that, you were doing, Kiran at IIT Hyderabad, that requires coordinated processing across transmission and reception across distributed base stations. So timing error they have to be aligned in time because the frames have to be aligned. So with TDD, it's indispensable. I would not say it's important. It's essential to have time synchronization. You can get that with GPS and, of course, the other equivalents of GPS like IRNSS. But, with the number of base stations, it's important that you derive timing from the backhaul network. And that's what I'm trying to emphasize here, that those working in optical networking need to rediscover how to distribute timing.
Good. So you touched upon 6G, but what's the main use case for 6G in your opinion?
Okay, that's a good question. I always love this question. Nobody knows is the correct answer. Okay, nobody knew. So I'll just take you to history. So 2G, the use case was supposed to be better voice, right? Digital voice, but the killer use case was SMS. 3G was, I think, some kind of special web browsing or some such thing. But really, BlackBerry and email became the biggest use case. 4G was simply about IP, was about IMS. Nobody thought of smartphone except Steve Jobs, and then 4G simply became about smartphone and apps and social media and all that, right? Which nobody thought. So similarly, 5G, we don't know. We think ultra low latency. So we haven't still figured out the use case for 5G. Maybe it is IoT, MMTC, URLLC. Otherwise, broadband-wise, it looks similar. So while we figure out the use case for 5G, 6G will find its use case in 2030. All we can say is that we are throwing a lot of bandwidth. So we should think of, so the standard use cases are, AR, VR, holograms. We could potentially be having this with all of us being present in 3D. I think that's all we can imagine today. So I think it's up, and I think the set of people who will figure out how to use all this bandwidth to do cool things are probably in primary school today, and they will figure out how to do this. So the real answer is we don't know, but there is so much bandwidth we are throwing at it But hopefully there will be stunning use cases that will emerge.
Excellent, excellent. So let me go to a different topic. There was a brief mention of ECPRI and ORAN in the context of Fronthaul.
Yeah.
With all the all the talk about ORAN, what is the role of system integrators, vendors, and operator deploying ORAN? What is your take on it, especially in the Indian context as well?
Okay. See, so far, I think it's well known that I don't need to hesitate. The entire RAN has been controlled by one vendor. So you could only, that means in one geography, you could only have one vendor. Because of interop issues, control, management, I think the core and the RAN being together got broken in 4G. So you had independent core companies, the likes of Cisco and all that. I think one of them acquired Starend. So they got into the core. So that got broken. But now to disaggregate further and so let's say break the radio from the distribution unit and the cloud unit, you need a completely open standard which is open with respect to control and management as well. So I think ORAN can play that role of creating a standard which is complete, which allows disaggregation. Disaggregation means you get multiple different vendors for different parts of the network, right? Different parts of the RAN, I mean, not one vendor for RAN, one vendor for optical, one vendor for core. So when that happens, then the operator will have to have the expertise to put all this together, right? And that many operators lack, and that's where the system integrators can come in. Because they have the expertise, they can build the least cost network, or even you can say the highest performance network, because they can buy the best radio unit, the best distribution units, the best optical, the best core, and so on, and put it together. And so I think disaggregating and betting on standards that allow different vendors for different parts of the network creates a better network overall, and also brings in system integrators because you need expertise to run these networks. So I think that's a good approach for India to take, to encourage disaggregation overall, okay, in the network.
Good. So I will, before I take questions from the audience, you have been the founding chairman of TSDSI. You have seen the society grow and evolve in the last 4 or 5 years. What do you think that TSDSI should be doing for the next 5 to 10 years?
Okay, I'll take the 10-year view because I'll be gone in 10 years, so you can't check if I was right or not. Okay, so, and anyway, net 2030 is 10 years away. We started because we didn't have an SDO. So we started, I don't remember exactly, but somewhere in 2015 or something we started. At that point, it was just to make a mark, to have an SDO, right? We didn't quite know what to do, except the goal was we'd go and participate in 3GPP under our own banner and not under HC. So we started with a modest goal, and then I'm very happy that we were able to make this RIT for 5G with the meeting the LMLC requirement. So that's good. So we made a small contribution. A new RIT is good bragging rights, but it's still, fairly small in the overall scheme of things. What I'd like TSDSI to aim, and India to aim, is that in 2030, we are a major player. So what's a major player? We have 10 years. And I think it's very doable that you get 10% of the essential patents in 6G in India. I think we could even potentially do more, but I think that is a very modest goal to set for ourselves. And we should be driving the full RIT. Or not, it may not be RIT anymore, it may just be as I said, 6G is not only about radio anymore, so not the radio interface technology, but the entire networking technology for 6G. So drive 6G and get at least 10% of the standard essential patents, maybe even more, simply because there is so much new to be done. I think as a country we can do that, and I see a lot of elements coming together. We have more and more of the countries getting connected. There's a lot of emphasis on Atmanirbhar and self-reliance and so on. So I think we can get there. So goal, drive the 6G networking into standard, make sure that we are behind the main proposal that gets adopted as 6G. Of course, we do it for the world, not just for India, and start inventing and patenting. That's not a TSDSI thing, that's like the whole community, and then TSDSI helps to get that into the standards.
Excellent. So that means the work has to start now, to make
yes.
Good comment. So what we will do is we'll now take up the questions from the audience. I would like to go with the I'll go from the last. Vipin Tyagi has the question: why packet-based synchronization, which supports nanoseconds, is not possible?
Yeah, so I think right now we have limitations in sort of the oscillator accuracy and all that you can get in the hardware. So that has to significantly improve before you can get to this time alignment error below 260 nanoseconds. I think it's work in progress, so we need to get to 65 nanoseconds, which is a factor of 4, but it will take some time. I think it's really to do with improvements in oscillator technology.
Okay. Next question. Using C-band itself, we can achieve several terabits of capacities using DWDM gridless. Why there should be a major concern on practical capacity limit on that? Can L-band also be deployed?
Okay, so the amount of spectrum available in C-band is really 80 channels of 50 gigahertz, right? So that's what I meant by 4 terahertz. So now 4 terahertz, depending on what you do with it, can, depending on the reach, you can do 200, 400 gig per that, right? So if you do 400 gig and 80 channels of 400 gig, that gives you 32 terabits. That's sort of the limit. Now, if you do L-band is practically the same as using another fiber. So this is of course per fiber, but then costs go up. Doing L-band is no different from doing another pair of fibers, which is building another network. So every fiber can be replicated. So that has an advantage which is not there in RF. But there is a lot of efficiency cost to be gained by running the same network in this 4 terahertz. Right? The 4 terahertz, if you can amplify, which we do, and then you should maximize the capacity there to keep the cost down. Otherwise, it's like building 2 networks. It will double the cost. Whether you use L-band or another fiber is the same thing. So the practical limits today are, I think I had a graph which I outlined. So 4 terahertz is what is there, and then depending on the distance, you could get 16 terabits, 32 terabits, and so on. Yeah. That's all.
Okay.
You're breaking up a little bit.
Can you hear me now?
Maybe you can mute your video. Okay, maybe I can look at the Q&A. Okay.
You can just look at the Q&A. I'll switch to.
Dr. Kumar, while you're waiting for the questions, one of the questions posed is by Dr. Rakesh Mehrotra on NAVIC is a solution for India, but can the world depend upon GPS as this can be manufactured by Department of Defense? Is it
yeah, so see, essentially every country is coming up with its equivalent of GPS. So India has NAVIC, I think it's also called IRNSS. Europe has its own, Russia has its own. So essentially each country will rely on its own set of satellites to provide that timing. And if you're a global supplier of equipment, you have to support all the standards. Let me go through the questions and answer them myself. Can you add more points on slicing support in backhaul? This is from Uttara Savant from Ericsson. Since radio is popular in slicing, it's interesting to know slicing interaction support in backhaul. See, 5G is end-to-end. So network slicing is end-to-end. So it's not good enough to support slicing only in the Fronthaul. So you need to do the same kind of dynamic scheduling of resources in the backhaul that you do in radio. So the optical and radio network has to be brought under the same SDN, if you will, software-defined network, and the services, the slices have to be provisioned end-to-end. So those technologies are just coming up. SDN is just getting adopted, but that's absolutely required. One second. What capacity has been achieved in WDM PON? I think this is again from Vipin Tyagi. NG PON 2, which is really also WDM PON, is 4 wavelengths of 10 gig, so that's 40 gig. But that's the standard, that's the last standard, but now newer standards are coming up to take it beyond. I've not kept up, but I think 50 gig PON per wavelength is coming up instead of 10 gig. So we will be able to see higher capacity PON networks. Okay, so Kiran, I did answer a few questions in your absence, but you can now pick.
Yeah, so I will ask you something, other than what the
Sure.
Doing scheduling and optical.
Yeah.
In wireless, we talk about doing scheduling in 500 microseconds, 250 microseconds. That's the limit. In optical, what are the time blocks available for physical processing?
So OTN, I forget what the OTN frame size is. Historically, all the time slots in optical were aligned to 125 microseconds. Okay, I mean that is simply because that was the voice standard. So I think OTN will give you time blocks of that nature at least. So you can get much smaller granularity than radio in terms of time. But remember that 125 microseconds in optical is a lot of bandwidth if you're running that at 100 gig. Yeah. To give a better answer to that, mostly in opticals, let's say if you take OTN, the minimum bandwidth available is 1 gigabit per second. So the slices will happen in 1 gig, multiples of a gig, 10 gig, and so on. In optical, we don't think less than a gig. Less than a gig is nothing. We just allocate 1 gig. Okay.
Yeah, interesting. Yeah. There's one question on what are the differences between backhaul and fronthaul in terms of configuration?
Oh, so Fronthaul is between the radio unit and the distribution unit. So typically that is high capacity, very sensitive to timing because the radio has to be clocked from the distribution unit. So that's Fronthaul, and the technologies used there are OTN, which is very good for timing and has high capacity. If you use packet networking, you must use time-sensitive networking because of the requirement of timing. Backhaul is from the distribution unit or today's cell tower. At that point, it's simply packet traffic, not very time-sensitive. You still carry timing, but you're not timing the radio unit. So that is, you could use IP, MPLS, and the regular packet technologies for backhaul. Next question.
Yeah, so I think pretty much we're exhausting the questions.
Okay, very good.
Let me see in the end. There is a question. Are there any plans to encrypt traffic on the backhaul?
On backhauls, yeah. So you can encrypt traffic on the backhaul. Typically, it is not required because the operators own their backhaul networks mostly, and therefore it's a trusted network. So you don't need to do any encryption on it. And anyway, user traffic has all the 3GPP encryption and so on. So it's not typical to encrypt in mobile backhaul, but military always likes to encrypt. So encryption is available. So you could encrypt the whole OTN frame or so on. You would probably encrypt over an untrusted backhaul network. So if you're using somebody else's backhaul network, you could potentially encrypt. But otherwise, encryption is not common.
Okay. Lots of questions coming in. We still have 5 minutes, so we can take some more questions.
Sure.
Some comments on IAB, Integrated Access Backhaul. This is a 3GPP term.
Okay. I know what that is. Okay. So this would be for the wireless backhaul portion. So if you recall my slides, I said there is wireless access, and there's the first step is a wireless backhaul, which I said was microwave, and then millimeter wave, and then now E-band. So I think integrating that wireless backhaul with the wireless access is a useful thing to do, because you do save on cost. You do save something on cost. I don't know how much, because anyway it's completely different bands. But if you use the same band, you will lose capacity, but then you will save on cost. So I think it's an interesting technology, especially for coverage reasons and low capacity. So if you need to cover remote areas, then in the same band, let's say 3.5 gigahertz, if you do access and use some portion for the first step of the wireless backhaul, I think that's useful to save cost. Okay, next question.
Yeah, there is a question on TSN. I hope we haven't taken that up before. Can you please give more details on the TSN? Is it the next generation NTP? What is the best timing accuracy one can get?
Okay, so TSN, so TSN is different from NTP, PTP, 1588v2 and all that, right? So those are protocols that you run end to end in order to synchronize a slave clock to a master clock. TSN's role is that these protocols, 1588 or PTP or whatever, have timing packets, which are small packets which are flowing through the network, and they get multiplexed along the user traffic. You may give them priority, but even if you give them priority, they can get stuck behind a 1500 byte packet or a 9000 byte packet. So what TSN does is allow for a large packets, the transmission of a large packet and link to be interrupted in order to send this high priority timing packet. So that's the new aspect of TSN, time-sensitive networking, is to interrupt the transmission of an ongoing packet and send a new incoming packet, which carries timing traffic. And that timing traffic is PTP and 1588v2 and all that. I hope I answered that.
This question keeps coming up. We still have 3 minutes. We should take this up.
Sure.
A candidate for mid and backhaul.
Okay. See, today satellite communication is very limited in bandwidth. So you'd sort of be choking what you're trying to do with 5G with SATCOM. So I would say, except for backhaul from remote areas, satellite is probably not a technology for, let's put it this way. If you get fiber, you get fiber. If not, you get terrestrial, microwave, millimeter wave. If none of this is an option, with a very remote area, the Sahara Desert or something, Mount Everest, then sure, then satellite is the only option. So I would say satellite is the last resort, not a preferred option.
Okay, we'll take probably the last question.
Yeah.
In the entire network of backhaul, midhaul, fronthaul, and end equipment in the 4G or 5G arena, any India-based component is used?
In the entire 4G backhaul, okay. So, that's a setup for my company. So we do make a lot of optical backhaul and fronthaul equipment. So in some sense, everything I talked about for fronthaul, backhaul, including GPON, OTN, packet transport, and MPLS, and so on, is something that's the business of Tejas. So I tried not to talk about my company, but thank you for giving the opportunity. Yeah. So we do make pretty much everything I described in today's talk in terms of fronthaul and backhaul equipment. So thank you.
Okay, so I think that will close at this point. I thank Kumar for an engaging discussion and an excellent view on the other side of radio, which is optical, which is very important. And we're privileged to have him speak today. With this, I will give to Bindu and others. Thank you.
Thank you very much, Dr. Kumar, and thank you very much, Kiran. Dr. Kumar, as always, your presentations simplify, demystify stuff, and considering that there were so many participants and the kind of engaging questions that were asked, I think the audience would have got some answers, and there would be some other follow-on questions or interactions, for which we encourage the participants to maybe reach out to TSDSI, and we could connect you with our experts. You can maybe consider joining TSDSI or attending our other workshops. We do run some roadmap workshops also, where we encourage people to, in general, contribute ideas and topics that you would like to take up. This series of webinars, this was the second webinar today. We intend doing running this webinar once every 3 weeks, 2 to 3 weeks or 4 weeks. The next webinar, we hope we're trying to fix the date for the webinar. The topic is likely to be on cybersecurity or on critical communications. Do watch out for on the TSDSI website for the announcement on the next webinar. And if you want to interact with the other fellow participants for this webinar, please stay back in the social lounge and enjoy interacting with the co-participants. With this, we bring the webinar to an end. Thank you very much. Thank you, Dr. Kumar.
Thank you, Kiran. Thank you, Bindu. Thank you all for attending. Have a good evening. Bye-bye.
Thank you. So the webinar social lounge will remain open for another 15 minutes till 19:15. So folks can stay back in the social lounge and interact with the participants.